So here we're going to review finding symmetry. Hopefully you've taken some time and read the notes and looked over the different cases and the criteria for testing symmetry, both in terms of an equation for symmetry about the y and symmetry about the origin, and also using function notation and testing symmetry that way, because that's what we're going to be using here. So we want to test each of our three symmetries: symmetry about the x, the y, and the origin. I'm going to begin here with symmetry about the y, because here I'm given a function, so I'm going to use my function notation and recall the criteria for symmetry about the y in terms of functions is f of negative x. When you replace x with negative x, it should actually take you back to the original function. So for symmetry about the y, we go ahead and evaluate f of negative x. So in other words, go into the f function, and everywhere you see the variable, replace it with a negative x. And so we do so, and we get 3 negative x quantity squared plus 12. Now remember, as we simplify here, a negative raised to the second power is just going to cancel out and become a positive. And so we're actually going to get 3x squared plus 12. And so yes, we do have symmetry about the y. Yes, we do have symmetry about the y. Okay. We then move on and do our second test for symmetry, which is symmetry about the origin. Now for symmetry about the origin in terms of a function, what we do is we replace the x with negative x, just like we did with the symmetry about the y test, except instead of it needing to be the original function, it needs to be the opposite of the original function. Well, we already know from what we just worked out that f of negative x is 3x squared plus 12. And that is not the negative of the original function. And so therefore, there is a big no there for symmetry about the origin. We don't have symmetry about the origin here with our function. The last one is symmetry about the x. Now we don't have a function test for something being symmetric about the x. If you look back to the notes, it's not a function. If you have symmetry about the x, you have given x's corresponding to multiple y's, and that just doesn't happen. So we don't have that. But the test is replace y with negative y in the equation. So instead of f of x, I can write it as y equals. So replace y with negative y. And if you can get back to the original equation, in this case y equals 3x squared plus 12, following basic algebraic rules for an equation, then you would have that symmetry. But here, there's nothing I can do to accomplish that. I could multiply both sides by a negative, but that's not going to do anything, because then the other side would be messed up. So that also gets a big no. And now we move on to our second example, which is not a function. It's not written in function form, at least. X squared plus y to the fourth equals 16. X squared plus y to the fourth equals 16. And in here, we want to again test our three symmetries: the y, the origin, and the x-axis. We can do them in any order. Here I'm just going to continue testing symmetry about the y. So I go into my equation, replace x with negative x, right, because that's the y condition. We did it both function-wise here, and now we're doing the equation-wise, replace x with negative x. And if we can get back to the original equation, then we have that symmetry. And so we can see here, well, negative x squared, when we simplify that, that'll just be x squared. And then y to the fourth was already okay, plus equals 16. And so we have symmetry about the y. We have symmetry about the y. Do we have the other symmetries? Well, we need to test and find out. So we check the origin. For the origin, in equation form, we replace both x and y with their negatives. And if we can get back to the original equation, then we have that kind of symmetry. Otherwise, we do not. So here, because it's being raised to the second power and being raised to the fourth power, the negative signs will disappear, and so we do have that symmetry. And then finally, testing symmetry about the x-axis. Remember, the condition is replace y with negative y. If we can get back to the original equation, we have that symmetry. And so as we can see here, we do in fact have symmetry about the x as well. Right? We have symmetry for all three in this case. Okay, so again, check those the notes, because it's explained out or diagrammed out how these different types of symmetries work, both in equation form, what you need to check, and in terms of a function, what you need to check.